Imagine these huge hidden currents moving deep in our oceans. Forces just immense, shaping climate, sustaining life, but totally invisible from the surface.
Right.
And one of the biggest, the Atlantic Meridional Overturning Circulation, the AMOC, it's like this massive engine for our planet's climate, often unseen, you know?
Absolutely. And what's, well, frankly a bit concerning is that scientists are seeing signs this crucial system might be faltering.
Faltering.
Yeah,
Huh?
some recent studies, some data, it suggests the slowdown could be happening much faster than we thought.
Mm.
Some estimates even raise the possibility, the risk of a collapse happening relatively soon.
Soon. Like, how soon are we talking? Because the system, it affects so much of our climate, the idea it might weaken significantly, maybe even collapse.
Mhm.
That feels like something that's kind of snuck up on people. We know past shifts were huge, linked to ice ages even.
Exactly.
But now we're here, this whole global society potentially facing it. It sounds almost like science fiction, like that movie.
Right. It does have that feel, doesn't it? Like
Yeah.
the day after tomorrow definitely put the idea out there in popular culture. Now, the really rapid, deep freeze like in the movie, that's probably not the most likely immediate outcome.
Okay, good.
But the real potential consequences, they're still incredibly significant. So that's what we want to do in this deep dive. Really get into the AMOC, what it is, how it actually works.
Including how it connects to those past climate shifts,
Yeah.
right?
Exactly. And the realistic impacts of a slowdown or a collapse and what these different predictions, sometimes conflicting ones, are really telling us.
Okay, let's dive in. What exactly is this AMOC thing?
Well, fundamentally, it shows just how connected our oceans are. It's not like separate ponds. It's one huge global system.
Right.
And the AMOC is a key player keeping it all connected. Think of it, one source called it a giant mixing bowl for the Atlantic.
A mixing bowl. I like that.
It's this incredibly complex system of currents, this sort of glorious giant vertical loop stretching right across the Atlantic, constantly moving water, heat, oxygen, nutrients, even tiny organisms all around.
A giant loop. So you're saying it's like a massive slow motion waterfall across the whole Atlantic, sinking at one end, rising somewhere else.
That's the core idea, yeah, the overturning part. Now, we hear about different currents all the time, right? Tides, surface currents.
Yeah, wind-driven ones.
Exactly. But the AMOC, its engine is really these much slower, deeper currents. They go from the surface right down to the seabed. And they're driven by changes in temperature and saltiness. That's what we call the thermohaline circulation.
Thermohaline. Thermo for temperature, haline for salt. Okay.
Okay.
So how does that actually work? How does temperature and salt drive this huge loop?
It's a pretty amazing cycle, actually. You have warm, relatively less salty water traveling north on the surface of the Atlantic.
Right.
When it gets up near Greenland, the Arctic, those colder regions, it gives off a lot of heat to the atmosphere, so it cools down.
Right, makes sense.
And at the same time, up there, when sea ice forms, the salt gets left behind in the water that doesn't freeze.
Ah, so the remaining water gets saltier.
Exactly. And colder water is denser. Saltier water is denser.
Yeah.
So this now cold, salty water becomes much heavier, much denser than the water underneath it.
And so it sinks?
Precisely. It sinks deep into the ocean, maybe thousands of meters down. Then it starts this long, slow journey back south as cold, deep water.
That's the overturning part.
That's the overturning. That
Yeah.
sinking in the north and the deep flow south. That creates the whole vertical circulation in the Atlantic. Eventually, way down south, that deep water mixes and rises back up, warms up, and completes the loop. It's like this global underwater conveyor belt, driven by how heavy the water is.
The sheer scale of that movement. I mean, the video we watched mentioned some numbers that were just hard to grasp.
Oh, they're staggering. Every single second, the AMOC is estimated to move about 17 million cubic meters of water north.
17 million cubic meters every second.
Every second. That's like, what, 7,000 Olympic swimming pools flowing past every second?
Wow.
And it's not just water. It's carrying an incredible amount of heat, around 1.2 petawatts.
A petawatt. That sounds like a lot.
It is. It's 100 times the entire world's energy production. All our power plants combined. It's this colossal heat redistribution system, like thousands of hurricanes worth of energy constantly moving.
But this whole incredibly powerful thing happens really slowly, doesn't it?
That's the paradox, yeah. For all that power, it's a very slow dance. Estimates are it takes about 1,000 years for a single parcel of water to complete the whole circuit.
1,000 years. Puts our timescales into perspective.
It really does. And that slow pace also means changes can build up over a long time before we see a big effect. It makes the system potentially sensitive to gradual disruptions.
Okay, so people often get confused between the AMOC and the Gulf Stream. How do they fit together? Are they the same thing?
Good question. They're definitely related, but not the same. The Gulf Stream is that warm, fast current that flows up the U.S. East Coast and then heads towards Europe.
Right, the one everyone knows about.
Yeah, it's a really crucial part of the AMOC, but just a part. Think of the AMOC as the whole circulatory system, the whole loop. The Gulf Stream is like a major artery within that system.
Ah, okay. A vital artery carrying warm water north quickly.
Exactly. The AMOC needs the Gulf Stream to bring that warm water north for the whole sinking process to work properly. But the Gulf Stream itself, that surface current, is mostly driven by winds and the Earth's rotation, part of this big rotating system called an oceanic gyre.
And it's the Gulf Stream that keeps Western Europe so much milder than places at the same latitude, like Canada.
Precisely. That heat transport is why, the UK has a relatively mild climate compared to, say, Labrador in Canada, even though they're at similar latitudes.
It's a huge difference.
Oh, yeah. Without it, the UK could be maybe 3 or 4 degrees Celsius colder on average. Mainland Europe, maybe 3 to 10 degrees colder. Huge implications for agriculture, everything.
Okay, so we've got this massive heat-moving AMOC, Gulf Stream as a key part. Now, the big concern, it seems to be slowing down. What's the evidence?
Well, one of the most striking pieces of evidence is this area in the North Atlantic south of Greenland that scientists call the cold blob.
The cold blob.
Yeah, it sounds a bit strange, but it's basically the only significant part of the global ocean that has actually cooled over the last few decades, while almost everywhere else is warming.
That is weird.
And it's not just on the surface. This cooling goes down deep, maybe 2,000 meters. It's a big red flag because remember, the AMOC's job is to carry heat north. If that transport weakens,
Then the area that usually gets the heat starts to cool down. Makes sense.
exactly. So the cold blob looks like a symptom, like the AMOC isn't delivering heat as efficiently as it used to.
Okay, the cold blob is one sign. Are there others pointing to a slowdown?
Yes, another really critical factor is the saltiness, the salinity, in that same North Atlantic region. Measurements are showing that it's declining.
Less salty.
Yeah, lowest levels in about 120 years of records. And that's crucial because less salt makes the water less dense.
And if it's less dense, it won't sink as easily.
You got it. It becomes too buoyant, it doesn't sink effectively, and that hinders the whole overturning process. It weakens the engine.
And where is all this less salty water coming from? Is it just more rain?
Rain plays a role, but the overwhelming scientific view points to increased freshwater runoff from melting ice, especially the Greenland ice sheet.
Ah, Greenland.
It's losing ice at a phenomenal rate, hundreds of billions of tons a year. All that fresh meltwater pours into the North Atlantic and dilutes the salty ocean water,
Making it less dense.
making it less dense. And plenty of studies using climate models and observations have directly linked this cooling trend, this warming hole as it's sometimes called, to human-caused reductions in that northward ocean heat transport. It all traces back to rising greenhouse gas emissions melting the ice.
It's this chain reaction. Warming melts ice, fresh water pours in, disrupts the AMOC's salt balance. Wow. How do scientists know if this slowdown is, unusual compared to the past before we had satellites and modern instruments?
That's where proxy data comes in. These are indirect clues about past climates hidden in natural archives.
Like ice cores.
Ice cores, yes,
Yeah.
and sediments from the ocean floor. Tiny fossil shells in those sediments, their chemical makeup, especially oxygen isotopes, can tell us about past water temperatures and maybe salinity.
Okay.
And the size of sediment grains can indicate how strong the currents were that carried them there by piecing together all these different proxies.
You can reconstruct the AMOC's history.
Broadly, yes, reconstruct its strength over time. And the reconstruction suggests a long-term weakening trend starting around the early to mid-20th century.
Which lines up with modern industrial warming.
It coincides pretty closely with the period of rapid human-caused global warming.
So, historical evidence seems to support the idea that our emissions are messing with this system. What are the specific climate change factors driving this instability?
Well, we've hit the main ones. Rising greenhouse gases causing overall warming and melting ice sheets, particularly Greenland.
Right.
But there's also Arctic amplification, the Arctic warming much faster than the rest of the planet. That changes wind patterns, which affects oceans.
Okay.
And then there's the water cycle itself getting more intense. More energy in the system means more evaporation in some places, more extreme rainfall in others.
Especially in the high latitudes, adding more fresh water up north.
Exactly. More precipitation up there, plus meltwater from sea ice too, although the big ice sheets like Greenland are the main freshwater source concern right now.
You mentioned a feedback loop earlier, the salt advection feedback. Can you break that down again?
Yeah, it's a bit of a tricky one, but really important. It's a self-reinforcing cycle. So the AMOC slows down because of fresh water.
Right.
A slower AMOC means it's bringing less salty water northwards from the tropics and subtropics.
Ah, because the current itself is weaker.
Precisely. So you get less salt arriving to counteract the freshwater dilution. That makes the North Atlantic even less salty, which makes the water even less dense.
Which slows the AMOC down even more. A vicious cycle.
That's it. Less salt leads to a slower AMOC, which brings less salt, which slows it down further.
It really sounds like a system balanced on a knife edge. Didn't someone figure this out ages ago?
Yeah, remarkably, the oceanographer Henry Stommel, back in 1961, he recognized this potential tipping point driven by salinity. He had this great quote, something like,
The Atlantic overturning flows because the northern Atlantic is salty.
and it's salty because the Atlantic overturning flows.
Yeah.
Perfect summary of that feedback loop and how easily it could be disrupted.
And this isn't the first time the AMOC has gone wobbly, right? The past holds some warnings.
Oh, absolutely.
Yeah.
The AMOC has definitely been unstable before. Its history is linked to some really dramatic climate swings, especially during the last ice age, but even during warmer periods like ours.
The video mentioned Dansgaard-Oeschger events. What were they?
DO events, yeah. They were these really abrupt, rapid warming spikes in the northern hemisphere, followed by slower cooling that happened over and over during the last glacial period.
Rapid warming during an ice age.
Sounds strange, but yes. And the evidence strongly points to AMOC instability as the likely trigger for these swings. The temperature graphs from Greenland ice cores show these incredibly sharp jumps. They often seem linked to other events too, like Heinrich events.
Okay, so DO events were these warming spikes from AMOC changes. What were Heinrich events? And the Younger Dryas?
Heinrich events were times when huge fleets of icebergs broke off the big North American ice sheet, the Laurentide ice sheet.
Armadas of icebergs.
Yeah, massive numbers. They floated out into the North Atlantic and melted, dumping enormous amounts of fresh water.
Just like the meltwater today, but maybe even more sudden?
Possibly, yeah. Huge pulses of fresh water. And that weakened or even shut down the AOC for a time, causing widespread cooling. We see layers of coarse iceberg debris and ocean sediments marking these events.
Then the Younger Dryas, that was more recent.
Relatively, yes. About 12,500 years ago, right as the planet was warming up after the last ice age, suddenly temperatures plunged back towards near glacial conditions, especially in the northern hemisphere, for over 1,000 years.
Wow. What caused that?
The leading theory is another massive freshwater pulse, probably from huge glacial lakes that formed as the ice sheet melted, suddenly draining into the North Atlantic, again disrupting the AMOC.
So clear evidence from the past. Dump fresh water into the North Atlantic, and the AMOC can slow down or stop with big climate consequences.
Exactly.
Which brings us back to the scary question. When might this current slowdown lead to a collapse? The predictions seem all over the place. Some say 2025, others say end of the century. Why such disagreement?
It's a reflection of how incredibly complex this system is and how difficult it is to model and predict. The IPCC, the main international climate body, had previously assessed the risk of a collapse this century as pretty low, less than 10%.
Okay.
Although even they acknowledged it could weaken significantly, maybe up to 46% by 2100, depending on emissions.
But we saw more recent studies sound a bit more alarmed.
That's right. Last year, a group of climate scientists issued a warning saying the risk might be higher than previously thought. And then there was that Nature Communications study.
The one that got a lot of headlines.
Yeah, estimating a potential collapse window between 2025 and 2095. They based that on analyzing sea surface temperature patterns going back to the 1870s.
2025 is startlingly close. But you mentioned there's debate about that study's method.
There is. It hinges on whether those sea surface temperature patterns are a reliable enough early warning signal for an AMC collapse. Climate models, like the ones the IPCC uses, are one tool. They simulate the whole climate system.
Right.
Some critics argue those models might actually make the AMOC look too stable, maybe not sensitive enough to fresh water. The sea surface temperature approach is different, looking for statistical signals in past data. But other scientists question if that signal is truly indicative of an imminent AMOC tipping point, or if it could be influenced by other factors. Plus, our direct measurements of AMOC strength from things like the Rapid Array.
That monitoring network in the Atlantic.
Yeah, that started in 2004. It hasn't shown quite the dramatic decline that some interpretations of the temperature data might imply. And the historical temperature data itself, based on old ship logs, has gaps and uncertainties. The authors of that study themselves acknowledge the uncertainties. to be fair.
So lots of debate about the exact timing and the methods. Is there any consensus emerging?
Well, while pinning down a specific year is really tough, the broad agreement among most scientists is that a major slowdown, or even a collapse, becomes increasingly likely if global warming continues unchecked.
So it's less if and more when if we don't change course.
That seems to be the growing consensus, yes. It's a question of pushing the system towards a potential tipping point. And even with the uncertainties, that Nature study pointed to a central estimate around 2070. Another paper suggested maybe 2037 to 2064, with a peak probability around 2050.
Those mid-century dates keep cropping up, still within many people's lifetimes.
Absolutely. It underlines the urgency.
Okay, so let's assume the worst happens, or at least a major slowdown. What are the actual consequences? The video painted a pretty grim picture.
Yeah, the impacts would be widespread and severe. Europe would likely face significant cooling. Average temperatures could drop, 3 to 10 degrees Celsius in just a few decades.
3 to 10 degrees, that's huge.
It is. Some places could see extreme winter cooling. Norway, maybe 35 degrees C colder in February, so that's likely a percentage rate of change. But still, the climate in Northern Europe, UK included, might start to resemble Northern Canada. Much harsher winters, more storms.
And less rain, right? Bad for farming.
Definitely. Significantly less precipitation predicted for Western Europe, which would devastate agriculture.
And it's not just Europe. What about sea level?
A weaker AMOC changes ocean circulation patterns, which actually affects sea level height. The prediction is for sea level to rise significantly along the Atlantic coastlines, maybe up to 70 centimeters in places.
70 centimeters, that's over 2 feet, threatening coastal cities everywhere.
Big threat. Increased flooding, erosion. And then there are shifts in rainfall patterns globally. The tropical rain belt would likely shift south. Meaning potential droughts in places like the Amazon rainforest, the Sahel region in Africa, but maybe more rain in other areas that are usually dry. It could also weaken critical monsoon systems, like in South Asia.
So massive disruptions to weather patterns and water resources worldwide. What about temperatures elsewhere? You mentioned the southern hemisphere might warm. That seems odd.
Seems counterintuitive, right? Cooling trigger causing warming. But it's about heat distribution. The AMOC currently ships a lot of heat north. If you slow that down, less heat gets transported north, so the North Atlantic cools. But that heat doesn't just disappear. It stays trapped more in the tropical Atlantic, the Pacific, the Southern Ocean. So the southern hemisphere could actually see accelerated warming.
And didn't you say it affects CO2 uptake?
Yes, the ocean absorbs a huge amount of CO2 from the atmosphere. That sinking water in the North Atlantic, part of the AMOC, carries dissolved CO2 down into the deep ocean, locking it away for centuries.
A natural carbon sink?
A vital one. If that sinking slows down, the ocean takes up less CO2, leaving more in the atmosphere, which could actually amplify global warming in the long run. So even the cooling in some areas isn't necessarily good. It's part of a massive destabilizing climate reorganization with more extremes everywhere.
The video mentions some complex effects on the Amazon too, maybe temporarily less stress.
Yeah, that's some nuanced research. Initially, a slowdown might slightly alter rainfall and temperatures in the Amazon in a way that could perhaps temporarily reduce some heat stress, maybe a slightly wetter, dry season.
But only temporary.
Very likely temporary, and highly dependent on how fast the rest of the planet keeps warming. Any small benefit would probably be swamped by overall warming trends. Plus, messing with the Amazon seasons, shifting rainfall patterns could be ecologically devastating in itself, even if average rainfall doesn't change much.
It's all interconnected in really complex ways. So, given how serious this is, how are scientists actually monitoring the AMOC right now? What are they measuring?
They use networks of instruments anchored to the seabed across the Atlantic. These are called moorings.
Underwater buoys with the sensors?
Essentially, yes. Arrays of sensors measuring current speed, direction, temperature, salinity, often from the surface right down to the deep ocean.
And those projects like RAPID?
Exactly. RAPID is a key international program, led partly by the UK's National Oceanography Centre. It's been measuring the Atlantic flow continuously at latitude 26 north since 2004. There are other projects further north, too, monitoring those crucial deep water formation areas.
So we're getting real-time data.
We are getting crucial data, yes. It gives us a direct measure of the AMPO's strength and variability. Monitoring that deep mixing in the north is also key, looking for signs that the sinking process itself is weakening. That could be an early warning.
But is the data definitive yet? Does it show a clear collapse coming?
The data shows variability and perhaps some signs of long-term weakening, but not yet a dramatic, unambiguous plunge towards collapse. We definitely need more data, longer records, and better spatial coverage to be certain about the trajectory. These monitoring systems are absolutely vital.
Okay, last big question. If it does collapse or weaken dramatically, could it just restart, bounce back?
That gets into this concept called hysteresis. It's a key idea for systems with tipping points,
Hysteresis.
meaning that once the system flips into a different state like a weak or collapsed AMOC, it might get stuck there, even if you remove the thing that caused the flip, like reducing the freshwater input.
It might not flip back easily.
Exactly. It might need a much bigger push, or conditions might need to return to a state far different from the one that caused the collapse in the first place, before it can recover its strong state. It doesn't just follow the same path back.
So it could get locked into a weak state for a long time?
That's the concern. Some climate models, like from the UK Met Office, suggest there might be a kind of resilience window, maybe 20 to 50 years after a certain point.
A window where recovery is possible.
Potentially, yes, if the freshwater forcing is reversed quickly and significantly within that window. But that window would likely be shorter if the freshwater input is really intense.
And what does the past tell us about recovery times?
Past events suggest recovery can take a very long time after a collapse, centuries, maybe even 1,000 years or more. And we have to remember, the situation now is unique. We have way more CO2 in the atmosphere than during past collapses.
And we're technically still in an ice age, just a warm phase.
Right. So those factors can change how it collapses and how, or if it recovers in ways we don't fully understand yet.
Okay, so wrapping this up, it really sounds like a major AMOC slowdown, maybe even a collapse, is a serious possibility within our lifetimes if we keep warming the planet like this. The exact timing is uncertain. That 2025 date seems like an outlier, maybe?
Likely an outlier based on current broader evidence, but the underlying risk is real.
But those mid-century timeframes, the 2050s, 2060s, 2070s, they keep appearing in different studies. It feels like a period of heightened risk.
That's a fair summary of the current scientific landscape, yes. While we can debate the exact year, the general trajectory under continued high emissions points towards increasing risk of crossing a threshold. The link is clear. Slow down warming, reduce freshwater input, and you reduce the risk to the AMOC.
It really hammers home that climate change isn't just about hotter summers or bigger storms, is it? It's about potentially destabilizing these enormous fundamental Earth systems that operate unseen.
Exactly. The AMOC is a perfect example of these critical, complex systems we rely on, often without even realizing it. Its stability is crucial for the climate we know.
And while the planet itself has survived huge changes before,
The planet will be fine eventually.
we haven't. Our civilization, this huge interconnected society, grew up in a relatively stable climate period. Facing something like an AMC collapse now, we just don't know how our modern world would cope with that scale of disruption.
That's the unsettling truth. It highlights how vulnerable our complex systems might be to changes in these fundamental planetary ones. The AMU is this intricate, powerful, and potentially fragile system. It definitely needs our urgent attention and, frankly, our care.